This video will discuss temperature and thermal expansion for solids and liquids. And discussing temperature involves sort of the concept of what temperature is. That will become a little bit more fully explained in a future chapter. But we do have devices that will measure temperature. There are physical changes that take place when temperature changes. And one example would be a thermometer with a bulb of liquid. As the temperature changes here, the volume of the liquid changes, and there's a small tube attached to this volume, and the liquid goes up or down the tube depending on the direction the temperature is changing. So one way to measure temperature with a thermometer, where the volume of the liquid is the mechanism by which the temperature is determined. Of course, we'll need calibration points. We'll talk about that a little bit as to how we standardize our temperature scale. Water is the common substance that's used to standardize our temperature, with 0 degrees on the Celsius scale being one standard, and 100 degrees, the boiling point of water, being the other standard. We won't use Fahrenheit very often in this class, but you should know how to convert back and forth from Celsius to Fahrenheit. There are 100 units between freezing and boiling on the Celsius scale. On the Fahrenheit scale, it goes from 32 for freezing to 212 for boiling. There are 180 units of temperature on the Fahrenheit scale between our calibration points, freezing and boiling. So 100 units on the Celsius scale, 180 units on the Fahrenheit scale. If you would make a fraction out of that, depending on which way you put the large number, you get 9/5. So if you do 180 divided by 100, there's a factor of 20 in both of those numbers, and you get 9/5. Now, it does turn out, if you multiply the Celsius temperature by 9/5, get that result, and then you add 32, you'll come up with the Fahrenheit temperature. Another system that will give us an indication of temperature would be a bimetallic strip, where the expansion of the two metals is different. As the temperature increases, we're seeing here the blue material has expanded more. The outside curve is a longer path than the inside curve, and consequently the material that expands more goes on the outside. But this would give us an indication of the amount of temperature change, and we can build devices like thermostats with this. If we put a mercury switch here and maybe make a coil of this material, but the metal moving, rocking back and forth, will either open or close the mercury switch and maybe turn our furnace or air conditioner on or off. Another mechanism that indicates temperature is the transmission of light. So if we put this little strip on your forehead, and 98.6 is your temperature, the transmission of this material increases, and the different strips, the light properties of it, the transmission of light properties changes in each strip to a different temperature. So at 95 degrees Fahrenheit, this strip is active. At 100.4 degrees Fahrenheit, this strip is active, and so forth. So it gives a rough indication of the temperature. Infrared light can be used. Now, this is not the infrared that is shining here, but have a little laser to point here where the human eye can see that, but the sensor is detecting infrared light and has equipment inside here to determine the temperature from the amount of infrared light at different wavelengths that is being radiated by this object. So the emission of light changes with temperature. There are other devices. The pressure of a gas changes as the temperature changes. The electrical resistance of some materials changes as the temperature changes. The volume, I've already mentioned for mercury, or for the thermometer, the volume changes, the length changes on that bimetallic strip. But all those thermometers need to be calibrated so that when you use different devices with the to measure the temperature of the same object, you get the same result. So the devices are calibrated to produce that. A little indication of temperature scales: the Fahrenheit scale used in the United States, the Celsius scale used on most places around the world, and it's more of a scientific temperature with 100 units between the two calibration points of 0 and for freezing and 100 for boiling. And then the best scientific temperature is the Kelvin scale, and we'll find that we're required to use Kelvin on some of the equations that we deal with that involve temperature. You should note that if we have 5 degrees change in the Celsius temperature, we'll also have 5 Kelvin change in temperature. The size of the Kelvin unit and the Celsius unit is the same. However, on the Fahrenheit scale, the Fahrenheit unit is smaller. It takes 9 degrees Fahrenheit to match 5 degrees Celsius. So there's your 9/5 coming in again. Here's infrared photography of a person, and the brighter areas are the warmer areas on the person. So that can have a medical application for determining improper blood flow or other problems that might be existing. This infrared photography is also used by utility companies to tell homeowners where they need some more insulation. Photograph the roof of a home from aerial photography, and the roofs that glow brightly are too warm and need more insulation to prevent, in the wintertime, that warm air going up to the roof. Little indication of different temperatures from the scale down here. Not a lot filled in here, but liquid helium, just a few Kelvin temperatures. Solar corona, about 1,000,000 Kelvin. The solar interior, 10 million Kelvin. Fusion, center of the Earth, so forth and so on. Quite a range of temperatures occur in our universe. So that's a little indication there. Let's go to this graph. So the graph here is plotting pressure versus temperature for a situation when the volume is constant and the number of molecules in the chamber is constant. Then there is a relationship between the temperature and the pressure of a gas. And if we do this for different species of gas and extrapolate, the gases are going to become liquid back here where these dotted lines are. But while they're still gases, we get a straight line, and if we extrapolate back, they meet at a point of minus 273.15 on the Celsius scale, absolute zero. They would have zero pressure. Expansion takes place on metals, so bridges on the two sides of the river. The bridge will have these interlocking fingers, and in the winter to summertime, as the bridge expands or contracts, the roadway will not be cracked because the fingers here will slide back and forth as the bridge expands and contracts. Volume expansion and area expansion shown here. If you cut a hole in a piece of metal and then you increase its temperature, the diameter of the hole will increase because the whole piece of metal is expanding, and this dimension here does not fill in. The hole does not fill in. Instead, the diameter gets bigger as the temperature increases. When we have a volume, the length, width, and height are all increasing as the temperature increases, so we'll have a greater volume. And there's some equations that we'll practice with that describe the change in the length, change in the volume. Water is an interesting material as the temperature changes towards the freezing point, 0 Celsius. As you look here, you see that the density of water is a maximum at 4 degrees Celsius. Why is it that small ponds freeze on the top in the winter and not freeze all the way through? Well, let's consider we have the pond at 6 degrees Celsius. The wind is blowing across the pond and cooling it down some more. As it cools down to 5 degrees Celsius on the surface, this material is more dense. It will sink down and push up water at 6 degrees Celsius until the whole pond is at 5 degrees Celsius. I'm just working in rough numbers. And then similar thing happens. The water at 5 degrees Celsius at the top cools down to 4 degrees Celsius. That's a little more dense. That sinks. Well, the pond all becomes 4 degrees Celsius. Then the top cools down some more to 3 degrees Celsius. That water does not sink because it's less dense. So the water at the top, 3 degrees Celsius, the wind blows across, cools it down to 2 degrees Celsius, to 1, to 0, and ice forms. And the ice forms on the top layer. The convection, natural convection in the pond stops once the pond is fully at 4 degrees Celsius. So that's why we get ice forming on the tops of water. Water is different than other liquids in that its density decreases as we near the freezing point. The way the water molecules pack together, they take up more volume, and the density goes down as the water approaches 0 degrees Celsius. And the fish are happy. They can swim in the liquid water that exists underneath the ice layer. The ice layer becomes sort of an insulator from the cold north wind. So interesting behavior of water. Our universe is designed to protect fish on the earth. Expansion and contraction. Okay, roadways have problems in withstanding that. This basically goes to the, again, length, width, and height increasing. We get a bigger volume. Air molecules being further apart as the temperature increases, becomes less dense, material becomes less dense, and it's not really the type of expansion that we're working with here for solids and liquids, but that's something that does exist. As the energy goes up, the molecules and atoms are further apart, they take up more space. That leads to the expansion in the linear sense, or also in the volume sense. Do you want to check your tire pressure as you go into the winter? As temperature goes down, the molecules are less active and bouncing off the walls, and the pressure can go down. But that's where we're going to stop here on this little video. Temperature, there is a way to measure temperature with various instruments, and you should not just say something's hot or cold. Different people have different opinions on whether a certain day is warm or cool. So you should use some type of scale, and Celsius is our first choice. We'll also use Kelvin, and Fahrenheit was just there for discussion to get some frame of reference, since in the United States we're more used to talking about Fahrenheit numbers. But you should work problems with Celsius or Kelvin, and you do need to be careful that you have the proper scale for equations in the future. And then as objects change their temperature, their length will change, their volume will change. So keep reading about that and ask some questions.